Well, we're going to move into design now. Again, the common factors affecting design of all the pavements. So right off the bat, we use permeable pavement really to achieve some combination of all or some of these three objectives. One is to reduce our impervious footprint. So if we're just trying to limit the amount of our site that's impervious, and so for those surfaces that need to be hard for whatever reason, we need to have vehicle access or pedestrian access, we can utilize the permeable pavement for those areas. And we then secondarily, flow control. So providing an opportunity to achieve infiltration, to serve those hard surfaces via the permeable pavement facility certainly is a key benefit. I think one thing that's really interesting about permeable pavement is it's somewhat forgiving on the infiltration front because it is such a large footprint. It really provides the opportunity for the water to be opportunistic in the base. So where you have maybe a bioretention cell is in one specific area, and we do our tests there. But permeable pavement is unique in that it can open up a really large area, which would allow to potentially unlock potentially unanticipated additional infiltration because the water will sort of seek its own path. And so with such a large footprint, I think that's a huge benefit. In terms of redundancy. And then of course water quality treatment. And so while the pavement section itself is not considered a water quality BMP, it can meet water quality objectives by infiltrating into the soil below. So if the soil below the facility meets the criteria for separation and for cation exchange capacity, then it can meet your treatment requirements. But that's an important distinction, that the actual pavement section itself is not, while however, I think research that Curtis has been reviewing for years from Europe and other places do show that there are quite a few active pollutant removal mechanisms in the section, and we're going to discuss that later. It's not as such considered a treatment BMP. Starting right in from the bottom up, slope sites, really these facilities want to be ideally flat. They want to be flat wherever we can to really maximize the water storage capacity in the base. With that said, I think we also want to make sure that we're grading these facilities to drain in a way that's fail-safe, so that if we do have some kind of a clog issue or something, that that the water is going to flow away from the buildings and in some kind of relatively controlled way. So I think subgrade can be maybe put in dead flat, but certainly the surface, I think we always want to make sure that we've got a little bit of controlled drainage generally away from the building. And as we increase the slope of the facility up to 5%, maybe as high as 8%, to achieve the storage volume that we need in that base requires the use of check dams of some type. This is showing a kind of a mounded soil check dam. I'm a little more of a fan of, and we'll see a detail of coming up, of a plastic liner type check dam, just because with the liner check dam you have the advantage of basically not compromising the section, not having any non-uniformity in the base rock. And so I think where you have these mounds as they're kind of drawn there, as much as we would want to kind of compact those, it would be a sort of a discontinuity in the base, and I would generally prefer the liner approach. Also, as we get steeper and steeper, in general, we do not want to see geosynthetics. We don't want to see filter fabrics under our pervious pavement, except in some really, really unique situations. And one of them, in my opinion, is in a particular, if you get into a steeper situation where you're concerned about scour, where you're concerned about velocity, moving, if the frequency of your check dams is such and the nature of your subsoil is such that you're concerned about scour, in those cases I have used, put a fabric down there basically as like an erosion control mat subsurface. Despite this image that you're seeing, which shows quite a bit of filter fabric underneath the pervious pavement, we really want to proceed with caution when doing that. This is a photo of the permeable pavement being installed up at High Point. So these details are discussing the whole issue of subsurface overflows. And I think it's a very, very important distinction to make, that we do not put under drains in under pervious pavement. We put subsurface overflows. But with that said, the way we detail these, so that we do not compromise the section, is we are placing that pipe submerged so that it's down below, so that we've got a full depth section above it, and that the elevation in that pipe is an outlet controlled pipe. And so I think that's a particularly important detail. that really gets to the idea that allows us to maintain a nice uniform storage layer. You can see there by the graphic is the invert of that pipe. I've set it in that case at 4 inches below my pavement as an overflow limit. And then looking at the section in the other view there on the lower right, showing how that detail can be incorporated into an internal check dam using a rigid liner. And so these are details that I drew that are from a project that I did on a slope and this particular approach. So you can see we've got the observation ports there so that we can pull the cap, we can look down in there and see, what whether we've got water standing in there and what have you. Really, their goal is to provide a controlled overflow to keep water from backing up into the pavement matrix itself, and it's an emergency overflow, and really providing a controlled flow path. So that same sort of thinking really should be applied to the surface as well, where we really want to understand when we're doing our grading, while we can be pretty close to flat if we need to be, we sort of make sure that we're fail-safe also. Geosynthetics are typically not necessary or advised, and they're typically not necessary under most permeable pavements. The issues that they can address, a subsurface scour issue, material separation in certain cases, maybe and you'll see on a little bit of a subsurface slope, if a base is sloped against a native soil, 95% of the time not advised, except for really special cases. And then moving up into the section itself, we've got now each of the systems are going to be different layers. Some have 2 layers, some have more. But in general, we've got our wearing course, which is going to be, whatever material. We've got the grids, we've got the permeable asphalt, permeable concrete. Some of the systems require a leveling course. Maybe the pavers, maybe asphalt. Sometimes is a leveling course required, sometimes not. I'll let others address that. But all of them include a aggregate subbase or a reservoir course below. And the reservoir course is generally sized for generally a flow control or a water quality, but an infiltration design. So it's designed, typically the depth is controlled for storage based on the voids, and generally section strength is generally not what controls that reservoir course. And then the geotextile, as we've already discussed. So the section design is applicable to each system. Each system will have its own criteria for sizing that wearing course. In the case of the pavers, it's fairly set in terms of the pavers, and again, the plastic grids. There are different sections available in the grids, and then the permeable concrete and asphalt is a little more based on a flexible pavement or a rigid pavement design process. But we also want to consider design speeds to understand what our appropriate use of our section, the appropriate thickness. Stress and torque on the pavement section. The main message here is we use traditional pavement design processes. Do factor strength down appropriately with each of the cases, but in general, we're using typical pavement design procedures. And then aesthetics, that's again, choosing our section. With our aggregate base, in general, we're looking for something with a 30 plus voids. And then looking at the diameter of the rock is important to understand, as getting to the last bullet there, about under pedestrian areas, typically a finer, smaller diameter drainage course can be used because of potentially the reduced base thickness. So if we're only going to have maybe 4 inches of rock underneath maybe a permeable sidewalk, we want to maybe use a smaller diameter material, so it's just easier to work with. But other than that, particularly if the base thickness is controlled by stormwater criteria, then often the bases can be the same between a permeable sidewalk and a permeable driving course, depending. And then low fines, and making sure we've got a clean aggregate base that isn't going to dump a bunch of fines and seal off our infiltration surface. So very often, washed out permeable ballast is used because it's commonly available, because it meets most of the criteria. It's got a decent fracture face, or when in a manufactured product, we're going to go with what manufacturers recommend, in particular for that choker course or that leveling course, which I think is a little more related to the product at hand versus the aggregate storage reservoir, which I think is a little more common. Now, we talked about, with Matt, reviewing our subgrade and understanding the characteristics of our subgrade. Pairing the subgrade is a critical design factor, and one that's probably, like I mentioned earlier, somewhat unique to permeable pavement, and probably an area where in the industry more learning is needed sophisticated or more industry advancement of understanding, because typically if we're going to do a traditional pavement, we want 95%, but 98% is better in terms of compaction, and if we wash out a few concrete trucks in there and just harden up that surface is generally our approach, what we want to do, but that is not the approach at all that we want to take with permeable pavement, of course. And so we really want to maintain the infiltration capacity that we've just measured through our process, and to maintain that, it's about getting just the right level of compaction and scarifying the surface so that we have a relatively irregular interface between our reservoir course and our subgrade. And then we mentioned geotextile again, probably not. And then setting the depth of that material, mostly probably based on hydraulics, but then also probably some minimum depth as well to make sure that our section is met. The whole issue of run-on is another one. Generally, the manual strongly discourages run-on, designing our pavements to receive flows from adjacent impervious areas, but it is done, but it needs to be done with caution, and then that will certainly affect the hydraulics of setting the thickness of the base. When we accept run-on onto our permeable pavement, we need to understand that we're going to radically change the O&M requirements. So in the example I mentioned earlier of the bike lanes in Bellingham, where they were installed for the purpose of acting like a big trench drain, the city vacuums them once a month because they're in our Lake Whatcom watershed, so they're serving primarily a water quality function, and so the additional O&M was understood from the beginning. In terms of how we model and how we account for these BMPs, pervious pavement, with respect to the new manual, the on-site stormwater management, List 2, the MR5 utilization of what's called List 2, which we don't get into too much detail, but we want to either select our BMPs based on List 1 or List 2, depending on which minimum requirements apply, and that's in the manual. That is where we're typically considering permeable pavement right at the top of the list for all new hard surfaces. And so we want to select them that way, or we can meet the LID performance requirement by essentially detaining to a level equivalent to what is considered the LID duration standard, which typically results in pretty large flow control facilities, and that in general, if your site meets the feasibility criteria for pervious pavement, it's typically going to be advantageous to use permeable pavement. To meet MR6 for treatment, we want to show that we're infiltrating at least 91% of the average annual runoff volume down through the soil below. So we will probably, in that case, if we were designing permeable pavement, just say we're just going to meet MR6, we would set our subsurface overflow elevation. You saw there, set the invert of that overflow pipe at a depth above the base that will give us a certain volume, and that we can run our gravel trench module in WWHM and show that we're getting 91% infiltration before the level in that base engages that overflow. And then if our soil below meets the criteria for the cation exchange and separation, Matt has given us the appropriate rate to use. That's essentially how we can model for that. And, similarly, for flow control, we can model that gravel trench element in as either we can be fully infiltrated, you know, if our rates are such that we can be fully infiltrated, or we can plug that permeable pavement in as an element, as an infiltration element into our model, and then it can do all or part or some of our flow control for that element. There are many other flow control standards, needless to say, that can be used if you're in some sort of a capacity controlled basin where you've got a certain maximum release rate or what have you. The key is to basically model the permeable pavement system as a gravel trench, where the gravel trench receives a tributary basin which is equal to its same size. Make sure that we don't have additional rainfall coming onto our gravel trench. We want to make sure that the module is excluding direct rainfall into the trench itself, but that it is essentially, we've got a tributary area of 10,000 square feet, and we've got a gravel trench area of 10,000 square feet. We can get fancy if we want to, put orifice controls on the base, which sometimes can be done, and then it's just a question of coming up with a stage storage discharge table type approach. But it's generally permeable pavement is modeled as a gravel trench. When we get into slopes, this is where we want to essentially look at the average depth between our check dams. So you can see in the image there, we've got depth 1 and depth 2 between our check dams. So we go ahead and average those and come up with a average depth multiplied by our void ratio can give us the characteristics of an equivalent gravel trench that is under there. And so then we take our tributary area and so apply it to that gravel trench, that average depth, and then we can start to size. And so depending on how our model goes, if we wanted to be fully infiltrated, then what we would look at the frequency of those check dams and the slope and the depth of our reservoir, and we would optimize those characteristics to come up with the right depth of gravel trench to achieve full infiltration, and then we can remove that area from the model. Or if our geotech tells us that we only can get a relatively small infiltration rate, and we decide that we're just going to use that permeable pavement for water quality treatment, and so we're just going to infiltrate 91% in that area, and then we're going to route the overflow to a flow control facility. Anyway, we can optimize that situation by looking at the geometry there and then setting the depth of our base rock to achieve whatever criteria we're trying to meet. There's a couple of key design details. We want to be conscious about transitions between permeable and impermeable pavement. We are concerned about undermining the fines out of the pit run that's underneath our solid pavement. And so we want to be really conscious about those transitions. My goal in all cases, if I can possibly get it to happen, is to have any transition between impervious and permeable pavement happen at a crown situation. So if I'm designing a parking lot and I want to have a transition, I want those transitions to happen at a crown point so that I'm not really concentrating much in the way of water at that interface. Where I can't do that, or if I want to really protect the impervious pavement from undermining, a couple things you can do. You can see in the detail there that I've done this approach where I've actually put in a vertical liner, like a piece of reinforced liner, vertical in there just to maintain separation. I've done flush curbing, so kind of a full depth flush curb, which would be like the most bomber transition. But I think at least being conscious about whether you're going to let the permeable base rock flow under the impervious pavement, maybe with a little bit of fabric on there to keep those materials separated if you wanted to have that trapezoid go under. But I think having some sort of barrier is advised, and having that transition be at a crown also advised. And then thickening the edge. So to avoid an edge failure, this is showing permeable concrete. But having that thickened edge allows, strengthens that edge for kind of a cantilever edge failure. It also allows what I think is another important detail there, which is to have the landscaping to really be intentional about the transition. If you're not going to have a curb there and you want to have that flush, that you really have your landscaping coming in probably 2 inches down, so that you really are going to keep those landscaping materials in the landscaping area and not have them migrate onto the pavement. Very often when I've had that detail, the landscapers will come and of course mulch it all up and over, and then the material's migrating out. So I think it's a key kind of a final punch list item very often to go out and talk about, or a inspection opportunity to come in and say, well, what is our top of mulch, top of planting soil, and make sure that that stuff is down and away to keep it from migrating and contaminating the pavement.